Taking a closer look at symmetrical vertical curves, there are some functions one can use to solve the elements. Let's derive them here in engineering surveys. According to their design, there are again two types of curves. The first one is symmetrical curve. These are those which are not really symmetrical, but then, when the horizontal distances are measured, symmetrical parabolic curves have the horizontal length from PVC to PVI as equal to the horizontal length from PVI to PVT. We can then say that the total length of the curve is equal to L1 plus L2. Let's illustrate this definition. Assuming that there are two tangents, the first is called back tangent, followed by the forward tangent. A highway is to be constructed, thus a curve is designed to connect them. The rising tangent has gradient 1, and the descending tangent carries gradient 2. As defined earlier, from PV1, the horizontal distance to the left is L1, which is equal to the horizontal distance to the right, which is L2. The vertical distance from PVI to the curve is h, and this is the same as the distance from the curve to the chord. There is also the highest point of the curve, and this is from S1 distance from PVC and S2 distance to PVT. The vertical distance between the highest point and PVC is then labeled as H1, and the counterpart is H2 from PVT. Then taking reference from PVI, the vertical distance of PVC to PVI is A, and PVT to PVI is B. A is the algebraic summation of the gradients, thus G2 minus G1 due to the change of directions. One question that may make you wonder is how to get the highest point of the curve. With the same background as shear and moment diagrams from strength of materials, there is also a grade diagram in highway engineering. Instead of loads, use gradients. So positive G1 means there is an upward gradient which connects to the downward gradient G2. Note that the point of inflection in the grade diagram is the location of the highest point in the curve, which means the location can be solved through similar triangles or ratio and proportion. The main character of symmetrical curves is L1 should be equal to L2, thus calling it a symmetrical curve. Now let's check how to come up with distances A and B. The derivation comes from gradient, which is rise upon run. By using the triangle formed with L1, we can take gradient G1 as A over L1. Then, by cross multiplication, A is then G1 L1. And again, in symmetrical parabolic curves, L1 is half of the total length of the curve. So plugging this into the equation of A and rearranging terms, we get A as half of G1 times L. The same process is used to derive B. We are using the triangle with L2. Gradient 2 is taken as B upon L2. So B is then G2 L2. And since L1 is equal to L2, L2 is also half of the total length, making B as G2 times half of L. Then B is half of G2 times L after arranging terms. In looking for the highest point in summit symmetrical curves, or lowest point in sag symmetrical curves, we use the grade diagram. From the simple illustration, we employ similar triangles, taking S1 is to G1, and this is equal to S2 is to G2. This proportionality can also be paired with another in order for us to add in the length of the curve, as this is usually the one given. Take another triangle which covers the whole length L, and the ratio in this is L is to the summation of the heights G1 and G2. From these combinations, we can extract the first pair with S1 over G1 as equal to L over G1 plus G2. Cross-multiply G1 to isolate S1, which becomes G1 times L over the binomial G1 plus G2. Then also use the pair of S2 over G2 with L over G1 plus G2. Isolate S2 again to have G2 times L over G1 plus G2. Take note that S1 is the distance of the highest or lowest point from PVC. Then S2 is the horizontal distance of the point to PVT. After knowing the horizontal location of the highest or lowest point, we also figure out the vertical distance of this point on either PVC or PVT. The derivation again uses the grade diagram, and just like shear and moment diagrams, the vertical distance of the parabolic curve is then solved by taking the area of the grade diagram. This is the area method in illustrating shear and moment diagrams. So taking the first area from the left, H1 is half of the base S1 with the height G1, and H2 is solved as half of S2 with G2. Next is solving for the maximum offset H. This is the vertical distance from PVI to the curve, which is also the distance from the curve to the chord aligned with PVI. To derive the function, we use similar triangles, but the triangle involved is with the extended back tangent all through PVT. The height created from PVT is L2 times G1 less G2. The computation was explained in the previous video. With PVC as the vertex, we can create the ratio of 2H is to L1. Then have this proportion with a bigger triangle, having L2 times G1 minus G2 upon L. Since this is a symmetrical parabolic curve, L1 is equal to L2, which is also equal to half of L. Convert all lengths into L, so we get 2H upon half of L is to L over 2 times G1 minus G2 all over L. Simplify the function and take out L from the right to arrive at 4H over L as equal to half of G1 minus G2. Take H as an eighth of L with G1 minus G2. We just derived the maximum offset, but how about the vertical offsets of any point from the tangent or curve? Since we are dealing with a parabolic curve, we use one of its properties, which is the square of the distances from the point of curve or tangency. If the point lies on the left half, we use PVC, just like in our example. Take the ratio of x squared is to y. Then equate this with the square of L1 over H. Then again, L1 is equal to L2, which is also half of L. So the proportion becomes x squared is to y as equal to the square of half of L over H. Arrange the terms to have y as equated to H with the square of x all over a quarter of L squared. Flip the denominator of the denominator up to have y is equal to 4 times H with x squared upon L squared.